H index. Given an array of integers where the ith element is the number of citations a researcher has received for their ith paper, return the researcher's H index. According to Wikipedia, the H index is defined as the maximum value of H such that the given researcher has published at least H papers that have each been cited at least H times. So the maximum H such that there are at least 8 papers that are at least have been cited at least H times. So in terms of our input, the maximum number of elements where their values are greater than or equal to that number of elements. That's kind of weird, but all right. Okay. So let's think about this. It looks like the input is very unsorted, so I'd expect our runtime to be at least linear. Let's see, the first solution I can think of off the bat is, okay, suppose you sorted this. That would be n log n time, assuming merge sort. You can receive faster average runtimes, but you can't really do better than n log n asymptotic, like worst case runtime to sort. Okay, so sort that, and that becomes, so suppose we have an input of 30615, and then we sort that to become, and we do it in reverse order, so 6, 5, 3, 1, 0. Suppose it becomes that, then we have some array. What do we do? Yeah, okay, we basically step through, okay. This first element, we have at least one paper that's been sorted, or cited at least 6 times, okay? Then we have at least 2 papers that have been cited at least 5 times, at least 3 papers that have been cited at least 3 times, and at least 4 papers that have been cited at least 1 time. Well, the H index is capped by the number of citations per paper, so there's really no sense continuing past the point where you have equilibrium. So 3 papers, each cited 3 times, that's our solution. That's the maximum H value we can get. So it goes 1. So the number of citations decreases while the number of papers increases, and where those 2 lines cross. So 3 and 3, that is the solution, output 3. So that would be n log n for the sorting, and then linear time for that second pass to go ahead and do that search there. I suppose you could do a binary search on it, and then you'd have log of n time for the second pass, but that wouldn't help with the asymptotic time because you still have n log n for that sort step at first. Can we do better? Yes, we can. If you accept a cost of linear space for allocating another array. So, okay, for example, this first approach I talked through, you could reuse the input and get constant space. Or if you have to make a copy, then you have linear space. The fastest approach where you can achieve linear time, that always has to use another array. So in that approach, if you get some table, so I'm going to call it T, and then it starts out is kind of like this. What you do is you fill it with, okay, so position 0, how many papers have been cited at least 0 times? Sorry, not at least, exactly. How many papers have been cited exactly 0 times? Well, we got 1 of them. So that becomes 1. How many papers have been cited exactly 1 times? Well, we got 1 of them. How many at least exactly 2? No papers have been cited 2 times. And then 3, we got 1 of those. 4, we got none of those. 5, we got 1 of those. And then if you clip anything larger than 5, because the maximum index is 5, if you clip anything larger down to 5, you get 2 in that last element. Because your H index can never be larger than the number of papers you've published. And in this case, what we would do is we'd sum so go from right to left. So we got 2. That is index of 5, that's greater than 2. Okay, we're looking for like kind of an equilibrium. And here we're comparing index of 4 versus the cumulative sum there, that's 2. 4 versus 2, no, we keep going. And then we have index of 3 versus the cumulative sum, so 3. 3 versus 3, well, we're not going to improve by continuing, so then we break there. Yeah, and that's pretty much it. I'm going to go ahead and start coding it. Okay, so the first step where we need to create that table, so we're going to have a vector of integers called t. And I'm going to initialize it to be, since we're also counting the number of papers that have been cited 0 times versus the number of papers themselves, like there's this mismatch here. So the table needs to be 1 bigger. I'm going to use temporary variable, I guess, so int n equals citations, because that's a mouthful to write out. So n elements, and they're each going to be initialized to 0. And then we do our first pass, so 4 int, and then we have a papers. We have, okay, so each citation element paper in citations. We need to deal with the clipping first, so c equals min of itself, or n. And then we increment. So then t of c plus equals 1. That's our first pass. Second pass to do the cumulative sum. So 4 int I equals, and then, okay, so our table size is, that table size should be n plus 1 actually, because we want to include that 0 index, so it needs to be a little bigger. Okay, so I going from n, so the last element in this table, down to 0. What do we do here? Okay, so in this case, we want to do our cumulative sum, so we have some return value, and we need to add it, so ret plus equals the value in the cell. And we need to check for equilibrium to conditionally break. So if I is less than the return value, we want to break sooner. So we need this. This will break us at a slightly bigger I. Return net. And then we have an error condition down here. So if we make it this far, we've got something wrong. Okay, let me think about this. So we did this example to start off with. So now I'm going to run this example. But first I'm going to talk about time and space complexity, which I already did, but I'm going to write them down. So we have O of n time and space. And that's because we have, okay, that's constant time. This is the linear time to allocate and initialize this temporary vector. Then we have a linear time loop here that does a constant operation, constant, linear time loop. This is constant, this is constant. Okay, so that's our runtime. Maximum is linear, and then this is also space complexity. All right, cool. So now, let's do example number 2. We've got 1, 3, and 1. And then our array t is going to be, it's going to be 0 to start up. Okay, so in size vector, okay, we initialize this, and then we go through the loop. So c, we're going to clip it. So 1, 3, 1. That looks like the clipping is never going to apply to any of these. Okay, so then we go ahead and increment. So t of c, so t of 1, that's 1. And then the third index we're going to increment, and then this first index 1 we're going to increment again. 0, 2, and 1. So that's our table. Now for the second pass. So then we go through and we've got some return value. So say I is that starting at 4 and return value starts at 0. I is 4. Okay, so return value, we're going to add 1 to it. And then we're going to compare. 1 is greater than or equal to, 1 is greater than, wait. If I is less than or equal to return value, that is not the case, so let me continue. We have 0 is, and then this, okay, that 3 is not less than or equal to, okay, now 2. We're going to add 2 to it. So 2 is now less than or equal to 3, but we don't want 3, we want 1 as our maximum because that's the actual values there. So now we've got, okay, we kind of found our equilibrium, but I need to solve this somehow. What I think I'm going to do is instead of returning the root value, I'm going to return the minimum between it and the index. Because really, okay, so H is the smaller of the number of papers and the number of citations. So red is the number of citations, and then we have I for the number of papers. Okay, so it's the smaller of the two. I think that makes sense. Would that affect the first test case? No, I don't think so. Because we would break after this anyway. That's not going to change. Let's see. We'd immediately find where 3 and 3 are equal, so that's okay. This will work fine on cases where that actually is the same. And then, okay, yeah, cool. Okay, let's see. Am I missing anything else? No, I don't think so. I'm gonna go ahead and give that a run for syntax. Cool. All right, nice. And go ahead and submit. Yes. Cool. You folks have a beautiful evening.